Hello, and good day to all of you. So, I'm here to present our paper entitled The Design of an Azimuth Altitude Dual Axis Tracking System, or AADATS, for energy solar harvesting using a photovoltaic V-trough concentrator. Here are the proponents of the paper: Concepcion Nathaniel, Delumpines Andrew, Villanueva Arnedo II, yours truly, the presenter, Michael C. Pasis, and my faculty colleague, uh, Glenn V. Magwili. And we are from Mapua University, Intramuros, Manila, Philippines, for the ICSGRC 2020 conference. So I want to share with you the presentation outline. So the presentation outline will begin with the introduction, and then methodology, and then the design of the system. Then we have the results and discussions and the conclusions. So to start with, as a developing country, the Philippines needs more sources of energy. The harsh reality that we now face is most of our electricity uses non-renewable sources of energy. If we continue this route, it is possible that we run out of fossil fuels, which is 50 years from now. But we can address our reliance on fossil fuels by developing our current renewable energy. Now, in the Philippines, since it is a tropical country, has a great geographical advantage. We can focus more on solar energy technology. So solar concentrators are more commonly used to improve the performance of solar cells and to absorb the maximum amount of sunlight that it needs to constantly face the sun. So we use a solar V-trough and integrating with a dual axis tracking system. And thus the tracker can help to do this efficiently, which we need the absorbance of sunlight, or we can produce more solar energy. Now, for this problem, so how can we constantly face the sunlight or sun rays using the AADTS and solar V-trough? So the objectives is we need to develop a solar concentrator system with the integration of the AADTS tracking system. So the sub-objectives are to implement the V-trough design. So we need to design the solar concentration first, or concentrator rather first, and then we integrate it to the design of the AADATS system. And then we need to determine the performance curves, wherein we can see the performance of the tracker with the solar V-trough, or tracker only, or no tracker and no solar V-trough. So from there, we can compare which of the following system can have a good harnessing of electrical output. So scope and delimitation, so it will not cover larger applications. So we only covered residential customers. So the degradation of the life years or the age of the equipment will not be considered here. All of the parameters are brand new and well designed. The significance of the study is we can provide an alternative way to produce higher energy outputs compared to an ordinary PV system. Now we have a solar tracker, plus from the solar tracker, we have a solar V-trough. So from that, we can expect that we can have a higher energy output. So let's go forward to the methodology of the study. Okay, first, on the input side is the sun, is the main source of the energy in the system. So it is constant movement of the sun throughout the day and is the most challenging aspect in harvesting its energy. So the issue we'll be addressing here is by using a dual axis tracker, which can help continuously tracking the sunlight from from north to south or east to west. So that's why it is a dual axis tracker. In addition to this, now we have a V-trough concentrator, as we have already explained, that we can use to absorb the maximum sunlight. So since we have a tracker and absorbing sunlight using a specific design, we can expect a higher energy output. So the system is programmed to detect the decrease in sunlight and automatically change its direction to absorb the maximum amount of this sunlight. The system is controlled using a microcontroller as its main processor. It has two server motors will be used to control the motion of the system, and one is for the up and down, while the other is for the left and right. The PWM signal, from the microcontroller will actuate the motors to rotate as desired, so that the data gathered will be used to create the performance curves, which can be interpreted at the last slides of this video or presentation. So this is the working flow chart. So first, we need to build the V-trough concentrating system. And then from there, we need to integrate the AADAT with the low concentration TB system. Then we can test the phototype, and then we can troubleshoot by calibrating the sensors. We use an LDR sensors for this purpose. And then we can have the performance curve and we can use at least T-test or Anova Test for the statistical treatment of the comparative analysis of every cases. So we have 3 cases here that we can discuss in the next few slides. Okay, this is the block diagram. So the only variable input here is the solar energy received from the sun, and therefore the researchers create a system throughout the V-trough design. The angle between the mirror and the panel and the reflecting materials can be used. So once the reflecting materials are placed properly on the northwest side of the panel, we can integrate the dual axis tracking system that was designed. Also in this research, we will connect a load at the end of the system, which make it possible to have readings. So the first of the methodology is building the V-trough concentration system. So how we will build that? So first we have the load modeling. Second is the solar panel tracking and the preliminary design of concentrating elements. So this is the load modeling and battery sizing. As you can see here, that we have the model of the load, which is here is an LED 12 volt 8 watt concentrated connected in the panel. That a brand of Omni. And from here it has a watts of 8 watts, and we have the lumens of 800 lumens. So CRI here means the color rendering index of less than 80. So the formulas for the ampere hours, the autonomous hours, the total energy, which is very beneficial to the ampere hour of the battery. And from there, we have a 33.68 ampere hour. And based on the ampere hour rating of the battery, the researchers choose a 12-volt battery having a 33 ampere hour. Also, from the computations, the solar panel have the following specs. The maximum power is 60 watts, and the open circuit condition on the voltage and the maximum voltage, the short circuit current are already on the slide. So we have a 12 volt 60 watts tri-G monocrystalline solar panel is used for more absorption of the electrical energy. So the design of the concentrating elements, which is first we will have the solar V-trough. Now here we have the LPB means the panel height, XPB panel width, XO mirror width, LO mirror height, and the beta is the tilt angle. But the most important here is the KL ratio. Well, in the KL ratio is dependent upon LO all over LPB. And we also computed for the LO, which is using this formula here. So based on these formulas, we gathered that the angle based from the study of Burkhardt, which is reference number 1, the most optimal tilt angle, okay, that you can see here on the solar V-trough is 60 degrees. It can be 53, can be 66, but here we decided that you use a 60-degree angle so that uh, we use that to avoid a non-uniformity on the panel and as much as possible without increasing further the size of the reflectors. So instead of conventional flat mirrors, we'll be using an anodized aluminum sheet. So from here, from the design, we use here an anodized aluminum sheet. So the reduced weight because of the anodized aluminum sheets and initial tilt will reduce the power consumption of the motors. So integrating the AADT to the LCPB system. So we have the microcontroller here, and then we have the loop system, and we use the Arduino Uno 80 Mega 328 and a PID controller. So the feedback controller of the system composed of the Arduino and then that 80 Mega 328 together with the LDR and sensors and a variable resistor that will function as a voltage divider. And we have the PID controller as well, was applied to the dual axis tracker to ensure that the system function within its mechanical limits. And the PID controller will control the motor to prevent it from jerking that can cause the gear to fail. So this is the flowgram flow chart. So we have the LDR voltage input. Then from there, we can check the LDR inputs by calibrating it, and then the sun detector. And then from here, we can have the LDR in terms of the north and south so that the motor can move in a upward or downward position. Likewise, on this next flow chart, we check the LDR inputs as well so that we can see if the tracker can move west to east or east to west. So it moves the motor in the right position or even on the left position. So this is the construction of the dual axis tracker. So we have the sensors block and the design of the azimuth altitude dual axis tracker and the specifications. So this is the overall design of our prototype, integrating all of the parts. So we use the statistical analysis here by the mean, and we can use the standard deviation coefficient variation. Okay. So this is the results and discussion here. So we have 3 cases. The first cases is without concentrator and without tracker. Second is with concentrator without tracker. And third case is with both concentrator and tracker. So as you can see from the charging current versus the time, the third case, which is the with concentrator and tracker, yields the best results. So this is also for day 4 to 6, then 7 to 9. So the power consumption is also described here. And as expected, the with concentrator and tracker, okay, yields the best result. So first day, second day, third day, okay, they are we determine the results, and then we repeat it on trial 2 and trial 3 respectively. Okay, this is the comparison of the setups, okay, with the percentage changes. And we also use the energy harvested equations. And we have the energy curves as well. And we have the comparison of charging energy of the 3 setups. And we have the Anova test. Okay, based on the conclusions, so we have a solar installation that to include a specific solar panel rating, load modeling, and battery sizing to ensure a sustainable system. We add a solar concentrator so that it can increase the collection of solar energy. And last but not the least, the prototype is idea for residential customers with a small scale application. It can be served as an alternative for standard solar PV system at home. And based on results, it can harness a greater amount of electrical energy. So these are our references. Thank you very much for listening.